crazy, right? We see it every day. Water, it can be solid ice, or it can be liquid water. And then there's steam, which is a gas. And it all just depends on how hot or cold it is.
It is kind of wild when you think about it. Like, these super familiar materials almost have these different personalities or something, and the temperature just brings them out.
Yeah. And they change so much between these different states, these phases. Like, the properties are totally different, even though it's the same stuff at its core.
Exactly. It's a fundamental thing in material science, how a material can change phases depending on what's going on around it. And actually, that's what we're going to be diving into today, this whole world of phase diagrams.
Phase diagrams. Okay, before we get lost in the weeds, can you give us a simple explanation of what a phase diagram actually is?
Yeah.
Like for the folks who aren't material science experts.
Sure. They're like roadmaps. But instead of showing roads and cities, they show you all the different phases a material can exist in. Like, is it going to be a solid, a liquid, a gas? And it also tells you kind of like the recipe you need to get those different phases, like the composition of the material, like if it's a mixture of stuff.
So, like, instead of telling us if it's going to be rainy or sunny, it tells us if a material will be a solid or a liquid.
That's a great analogy, like a weather map for materials. And just like a meteorologist uses a weather map, scientists and engineers use these phase diagrams to figure out how a material will behave in different situations. Super helpful for anything from, like cooking a perfect steak to designing a super strong alloy for a spaceship or whatever.
Awesome. So we're decoding these material roadmaps today.
Hmm.
What sources are we using for this deep dive?
Mostly, we're going to be looking at this classic materials science textbook. Specifically, we're focused on Chapter 9, which is all about phase diagrams. It covers the main ideas really well, and it has good examples, even using everyday stuff like dissolving sugar in water, which actually follows the same basic rules.
Okay, learner, get ready for a deep dive into the secret world of materials. So, where do we even begin with these phase diagram maps?
First things first, we got to learn the lingo. Like, there are a bunch of key terms that we need to know to understand these diagrams. So let's start with component. When we talk about alloys, which are mixtures of metals, the components are the pure metals or the compounds that are in that alloy. So like if we think about brass, that's an alloy, and its components are copper and zinc.
Got it. So, like, the individual ingredients that make up the alloy. Okay, what's next?
Next, we got system. Now, this one can be a little tricky because it has two meanings. It can mean the actual specific piece of material we're looking at, like say, if we have a beaker full of molten steel, that's a system. But it can also mean the whole family of alloys that you can make from the same set of components. So like the iron-carbon system includes all different types of steel and cast iron, from low carbon to high carbon.
Okay, so system is either really specific or it's the whole big picture of a material family. Makes sense.
All right, next up is solid solution. Remember how we talked about alloys being mixtures? So imagine a solid material, right? And the atoms in that solid are arranged in this really organized pattern, like a crystal structure. A solid solution happens when you sneak in atoms of a different element, which we call the solute, into that already existing structure. Now, there's two ways they can sneak in. They can either like replace some of the original atoms, which is called substitutional, or they can squeeze into the little gaps between the original atoms, and that's called interstitial. But the important thing is the overall crystal structure of the original material, the solvent, stays the same. So it's like, adding a little spice to a recipe without changing the whole dish.
So the structure stays the same even though you've added something new.
Yeah, exactly. But here's the thing. For every temperature, there's like a limit to how much solute you can actually dissolve in the solvent. And we call this the solubility limit. Think about dissolving sugar in water. You can stir and stir and the sugar disappears, but at some point you just can't dissolve any more sugar. You'll have a bunch of sugar sitting at the bottom of the glass. That's hitting the solubility limit. And this limit changes depending on the temperature. Like think about iced tea versus hot tea, right? You can dissolve way more sugar in hot tea, and we can actually map out this solubility limit. Like imagine a graph where one side is temperature and the other is the amount of dissolved stuff. The solubility limit would be a line on that graph.
Makes sense. Solubility limit to the point where you just can't dissolve anything else. Okay, what else do we need in our material science glossary?
The next big one is phase. So a phase is any part of a system where the physical and chemical properties are the same throughout. Like any pure material, like pure gold or pure oxygen, that's a phase. And any solid, liquid, or gas solution where everything's mixed evenly is also a phase. Even if the chemical formula is the same, if they have different physical properties or different phases. Like ice and water are both H2O, but one's a solid and one's a liquid, so they're different phases. And then there's the crystal structure thing. Like some materials can have different crystal structures depending on the temperature. Those are also different phases.
Okay, phase equals consistent properties throughout.
Right.
So what happens when things aren't so consistent?
Well, then we're talking about homogeneous versus heterogeneous systems. If a system has only one phase, it's homogeneous, meaning everything is uniform. But if a system has two or more phases, it's heterogeneous, meaning it's a mixture. Like oil and water, that's heterogeneous.
Hmm.
A lot of the materials we use every day, like alloys, ceramics, polymers, those are often heterogeneous.
It's kind of cool how it's the mix of phases that makes these materials useful.
Yeah. And that brings us to microstructure. This basically describes how those different phases are arranged within the material, like how many phases there are, how much of each, what their shapes and sizes are, how they're all distributed. It's like the internal architecture of the material. And microstructure is super important because it determines the material's properties, like will it be strong, will it be brittle, will it be flexible, and it all depends on like what elements are in the alloy, how much of each, and how it was heated and cooled.
Microstructure, the material's internal blueprint.
Mm.
Okay, so we've got phases and how they're arranged, but what determines which phases form in the first place?
That's where equilibrium and free energy come in. Basically, every system wants to be in the most stable state possible. Like, imagine a ball rolling down a hill, right? It wants to get to the bottom to the lowest point. For materials, that lowest point is the state with the lowest free energy, which means it's the most stable. And when a system is in that most stable state, we say it's at equilibrium. At equilibrium, nothing's really changing anymore. It's settled.
Equilibrium, like the material's chilling out, right?
Yeah, exactly. But we can mess with a system's equilibrium by changing things up. Like if we heat it up or cool it down or change its composition, that's like pushing the ball back up the hill. And then the system will try to find a new equilibrium, a new stable state.
So phase equilibrium is just this idea of equilibrium, but with multiple phases.
Yep. It means that the different phases in the system are in balance with each other, and their proportions and compositions aren't changing over time. Like remember the sugar water example. If you have syrup in contact with solid sugar, and it's all at equilibrium, the syrup has the maximum sugar concentration for that temperature. But if you heat things up, the solubility limit changes, so some of that solid sugar dissolves until a new equilibrium is reached.
It's like a constant push and pull between the different phases.
Totally. But here's the thing. Sometimes it takes a really long time for a system to reach true equilibrium, especially in solids where the atoms are all packed in tight. And when a system gets stuck in a state that's not truly the lowest free energy, but it's hanging out there seemingly stable, we call that a metastable state. These metastable states can be surprisingly useful. Like a lot of high-strength alloys are actually in metastable states because of how they were heat treated. So it's kind of cool how sometimes a little bit of instability can make a material stronger.
So a stuck state can be a good thing. All right, so with all this vocabulary under our belts, what exactly is a phase diagram?
A phase diagram, which is also sometimes called an equilibrium diagram, is basically a graphical representation of what phases are stable at different conditions, like at different temperatures, pressures, and compositions. So it tells you what to expect a material to look like if you change those variables.
Okay, so now we've got our basic map reading skills. What kind of specific phase diagrams are out there?
Let's start with the simplest kind. One component or Unary phase diagrams. These are for pure substances, so the composition is fixed, it doesn't change. The only things we change are pressure and temperature.
And isn't the water phase diagram the classic example here?
Yep, exactly. Like, if you look at figure 9.2 in our textbook, you can see the phase diagram for water. You've got regions for solid ice, liquid water, and water vapor, all nicely labeled. And the lines between those regions, those are called phase boundaries. When you're right on one of those lines, it means that two phases can coexist at equilibrium. So like the line between solid and liquid, that's the melting point line, right? And any point along that line represents conditions where ice and water can exist together.
So if we move across those lines by changing the temperature or pressure, we're forcing the material to change its phase.
Exactly. Now, if you look closely, you'll see that all three of those phase boundary lines meet at one special point, and that's the triple point. For water, the triple point happens at a really specific temperature, which is just a tiny bit above freezing, and a really low pressure. And what's cool is, at that exact point, all three phases of water, ice, liquid water, and water vapor can exist at the same time in equilibrium.
Wow, the triple point where ice, water, and steam all find a way to get along. That's amazing.
Right. It's actually so well defined that it's used to calibrate thermometers all over the world.
So that super specific point is actually fundamental to how we measure temperature. Okay, and the outline mentions that other substances have their own phase diagrams too, right?
Oh, yeah. Every pure substance has its own unique phase diagram. And if a substance can exist in different solid forms, like different crystal structures, then its diagram will be even more complex because it'll have regions for each of those different solid phases.
Okay, Unary phase diagrams, they show us the different phases of pure substances. So let's move on to binary phase diagrams, which I'm guessing are a bit more complicated.
They definitely are. These are way more common in material science because they deal with alloys, which are mixtures of two or more elements. So instead of just pressure and temperature, we also have composition to worry about, like the proportions of each element in the alloy.
So it's not just pure water anymore. Now we're adding stuff to it.
Yeah, exactly. So a typical binary phase diagram will have temperature on one axis and composition on the other. And we can use these diagrams to figure out what phases will form in an alloy depending on the temperature and the composition.
So like if we're mixing copper and nickel, we could use a binary phase diagram to see what happens when we heat it up or change the proportions of copper and nickel.
Right. Let's start with the simplest type, which are binary isomorphous systems. What makes these systems special is that the two components can completely dissolve in each other. Like, they're totally miscible both as liquids and as solids.
Isomorphous, it sounds like it means same form, like they mix perfectly no matter what.
You got it. The classic example here is the copper-nickel system. If you look at figure 9.3a in the textbook, you'll see the phase diagram. You have three main regions on this diagram. One where the alloy is completely liquid, one where it's completely solid, and one in between where you have both liquid and solid present at the same time.
Okay, so why are copper and nickel such good mixers? Why do they dissolve so well in each other?
It's because they're really similar at the atomic level. Like they have the same crystal structure, their atoms are almost the same size, and they have similar electronegativities. So it's energetically favorable for them to just mix together completely.
Gotcha. They're like the best buddies of the periodic table.
Yeah.
Now, the diagram has lines separating those different regions. What are those lines all about?
Those lines are called phase boundaries. The line between the liquid region and the two-phase region, liquid plus solid, is called the liquidus line. Anything above that line will be completely liquid. And the line between the solid region and the two-phase region is called the solidus line. Anything below that line will be completely solid.
So the liquidus is where it starts to melt, and the solidus is where it finishes solidifying.
Mhm.
And in between, you've got a mix of liquid and solid.
Right. And if you look at the edges of the diagram where the liquidus and solidus lines meet the pure copper and pure nickel ends, those points are the melting points of pure copper and pure nickel.
Makes sense. So pure substances melt at a specific temperature, but for alloys, it's a whole range.
Yep. For example, an alloy that's 50% nickel and 50% copper, it won't melt all at once. It'll start melting when it hits the solidus line, and it won't be completely liquid until it reaches the liquidus line. So melting happens over a range of temperatures.
That's a big difference from pure substances. So these phase diagrams can tell us a lot about how an alloy will behave as we heat it up or cool it down.
Exactly. And we can actually use them to figure out some pretty specific stuff about an alloy at a given temperature and composition. Like we can figure out what phases are present, what the composition of each phase is, and how much of each phase we have. It's like having X-ray vision for materials.
That's awesome. So how do we actually use the diagram to figure all that out?
Okay, first, to figure out what phases are present, you just find the point on the diagram that matches the alloy's composition and temperature. Like if you have an alloy that's 60% nickel and 40% copper, and you want to know what phases are present at 1100 degrees Celsius, you just find that point on the diagram.
And whichever region that point is in tells you the phases.
Exactly. Now, to figure out the composition of each phase, things get a little trickier. If you're in a single phase region, then the composition of that phase is just the overall composition of the alloy. But if you're in a two-phase region, like where you have both liquid and solid present, then you got to use a special tool called a tie line.
Tie line.
Yeah, it's just a straight horizontal line that you draw across the two-phase region at the temperature you're interested in. And the ends of that tie line, they'll touch the phase boundaries on either side of the two-phase region.
Okay, so the tie line connects the two phase boundaries at that specific temperature.
Exactly. And where the tie line intersects each boundary, Those points tell you the composition of each phase at that temperature. Like where it touches the liquidus line, that's the composition of the liquid phase, and where it touches the solidus line, that's the composition of the solid phase.
Gotcha. So the tie line is like a ruler, and you use it to read off the compositions of the phases.
Mm.
What about figuring out how much of each phase you have?
That's where the lever rule comes in. It's based on this idea that the amounts of each phase are related to how far the overall composition is from each phase boundary.
Okay, that's kind of confusing. Can you explain it with an example?
Sure. Let's say you have an alloy that's 35% nickel and 65% copper, and you heat it up to 1250 degrees Celsius. If you find that point on the phase diagram and draw the tie line, you'll see that the overall composition is closer to the liquidus line than the solidus line. And that means that at that temperature, you'll have more liquid phase present than solid phase.
So the closer the composition is to a phase boundary, the less of that phase there is.
Exactly. And there's a formula you can use to actually calculate the percentages, which is basically based on the lengths of the segments of the tie line.
So the lever rule lets you figure out the proportions of each phase in the mixture. Cool. Now what happens when we cool an alloy down quickly? Does it always follow the phase diagram perfectly?
Not always. We've been talking about equilibrium conditions, which means that we're heating or cooling the alloy really slowly. But in the real world, we often cool things down much faster, which can mess with the microstructure.
And what kind of problems can happen with fast cooling?
Well, the main problem is that the atoms don't have enough time to diffuse and rearrange themselves properly. Let's say you're cooling that 35% nickel, 65% copper alloy from a completely liquid state. As it cools down, the first solid that forms will have a higher nickel content than the remaining liquid. But as more solid forms, the nickel content of the solid should decrease because the liquid is becoming richer in copper. But if you cool it down too fast, those nickel atoms don't have time to move around and even out the composition.
So the solid ends up with a kind of uneven composition.
Yeah, exactly. And we call that coring. Each grain of the solid will have a core that's richer in nickel, and the nickel content will decrease as you move towards the edges of the grain.
So instead of a nice homogeneous solid, you end up with these grains that have different compositions in different parts.
Yep. And that can affect the material's properties. The grain boundaries might be weaker because they're richer in copper, which has a lower melting point.
That doesn't sound good. Is there a way to fix this coring problem?
Yeah, you can do a homogenization heat treatment. Basically, you heat the alloy up to a temperature where diffusion can happen more easily in the solid state, and that lets the nickel and copper atoms move around and even out the composition.
So a little bit of heat can fix the unevenness caused by cooling too quickly. That's a handy trick. Okay, let's switch gears and talk about a different type of binary system. Binary eutectic systems. How are these different from the isomorphous ones?
The big difference is that in eutectic systems, the two components have limited solubility in each other when they're solid. So instead of forming a single solid solution across all compositions, they tend to form two or more separate solid phases.
So instead of mixing perfectly, they separate out.
Kinda. A good example is the copper-silver system. If you look at figure 9.7, you'll see that there are three single-phase regions. You have a region for copper-rich solid, a region for silver-rich solid, and a region for the liquid. And the lines that separate those regions, those are called solvus lines, and they show the solubility limits.
Solvus lines, they show how much of each element can dissolve in the other. Okay, and do these systems still have liquidus and solidus lines too?
Yeah, definitely. And they mean the same thing as in isomorphous systems. The liquidus lines show where things start to melt, and the solidus lines show where solidification is complete.
Gotcha. So what's so special about these eutectic systems?
Well, the key thing is the eutectic point. It's the point on the diagram where the two liquidus lines meet. And at that point, something really cool happens. As you cool the alloy down, the liquid doesn't just solidify into one of the solid phases. It transforms into both solid phases at the same time.
Wow, both at the same time.
Yep. And this happens at a very specific temperature called the eutectic temperature, and at a specific composition called the eutectic composition. And because it involves three phases, the liquid and the two solid phases all existing at the same time, it's called an invariant reaction.
So it's like a three-way intersection on the phase diagram.
You got it. And this simultaneous formation of two solid phases often creates a really interesting microstructure with these alternating layers of the two phases.
So the composition really matters in these eutectic systems. What happens if you have a composition that's not exactly at the eutectic point?
Well, then things get even more interesting. As you cool the alloy down, you'll first hit a two-phase region where the liquid starts to solidify into one of the solid phases. We call that the primary phase. And as you keep cooling, you'll eventually hit the eutectic temperature. And then the remaining liquid, which will now have the eutectic composition, will solidify into the eutectic structure.
So it's like a two-step process. First, one solid phase forms, and then the rest of the liquid turns into that layered eutectic structure.
Exactly. And the overall microstructure will have these primary phase grains surrounded by the eutectic structure.
Okay, that makes sense. Now, are there any other important reactions that happen in binary systems?
Yeah, there's the eutectoid and the peritectic reactions.
What are those all about?
The eutectoid reaction is kind of similar to the eutectic reaction, but it happens entirely in the solid state. So instead of a liquid transforming into two solids, you have one solid transforming into two different solids.
So it's like the eutectic reaction, but with solids instead of liquids.
Exactly. And this eutectoid reaction is super important in steels because it's how we get a microstructure called perlite, which gives steel its strength and ductility.
So we'll talk more about that in a future episode about steels.
Definitely. Now, the peritectic reaction is a bit more complicated. It's another three-phase reaction. But in this one, upon heating, a solid phase and a liquid phase react to form a different solid phase.
So you're basically melting a solid in a way that creates a new solid phase. That's pretty wild.
It is, and some phase diagrams, like the copper-zinc diagram, have multiple peritectic reactions going on.
These diagrams can get really complex. Okay, before we wrap things up, let's talk about the Gibbs phase rule again. How does that rule apply to all these different reactions and phase diagrams?
Well, the Gibbs phase rule is basically a way to figure out how many phases can exist together in a system at equilibrium. Remember the equation, P plus F equals C plus N.
Yeah, and we said that for binary diagrams at normal pressure, it simplifies to F3 phi P.
Right. So what that means is that the number of things we can change independently, like temperature and composition, depends on how many phases are present.
So if we only have one phase, we have more freedom to change things up.
Exactly. In a single phase region on the diagram, we have 2 degrees of freedom. We can change both the temperature and the composition without creating any new phases.
But if we have two phases, we can only change one thing independently.
Yep. Like, if we fix the temperature, then the compositions of the 2 phases are automatically set by the phase diagram.
And if we have 3 phases, we can't change anything.
Right. In a 3-phase equilibrium, like at the eutectic point, everything's fixed. The temperature and the compositions are all set.
The Gibbs phase rule is like the ultimate rule book for these phase diagrams.
Yeah.
Okay, one last thing before we finish. Can you give us a quick intro to the iron-iron carbide phase diagram?
Sure. This diagram is super important because it's the basis for understanding steels. The main thing to remember is that pure iron can exist in different crystal structures depending on the temperature. At room temperature, it's BCC, which is called ferrite. Then at higher temperatures, it transforms to FCC, which is called austenite. And then at even higher temperatures, it goes back to BCC, which is called delta ferrite. And when we add carbon to iron, it dissolves into these different crystal structures.
So pure iron changes its structure depending on the temperature, and carbon can dissolve into those different structures.
Exactly. And the iron or carbide phase diagram shows us what phases are stable at different temperatures and carbon contents. So it's the key to understanding how to heat treat steels to get the properties we want. But that's a whole other deep dive.
All right, learner, we've covered a lot of ground today. From the simple phase changes of water to the complex world of binary alloys, we've seen how these phase diagrams can help us understand and predict the behavior of materials. It's amazing to think that these everyday materials have these hidden worlds of phases and transformations happening all around us.
And it all comes down to thermodynamics. These phase diagrams are just a way to visualize the most stable states of matter under different conditions.
We only scratched the surface today, but hopefully this deep dive has given you a better understanding of these fundamental concepts.
And I encourage you to keep exploring. Look back at the phase diagrams in the textbook and try to trace the phase transformations for different alloys as you change the temperature. It's a fun way to test your understanding.
So the next time you see ice melting or metal being welded, remember those phase diagrams and all the intricate changes happening at the microscopic level.
It's a whole new way to appreciate the materials that make up our world.
Absolutely. And who knows, maybe we'll do another deep dive on a specific material system soon. Until then, keep learning.